Hi everyone, my name is Vincent Lostanten and today I'll be presenting self-calibrating acoustic sensor networks with per-channel energy normalization, or PCEN for short. But before we talk about machine perception, let me start by recalling the abilities of human perception in the presence of noise. A recent study by Julien Meyer and co-authors evaluated the intelligibility of shouted speech in a forest environment. They reported a classification accuracy of 75% for 17 French words at a distance of 90 meters. Now, despite the impressive progress of automatic speech recognition over the past decade, the current state of the art is incapable to match this ability of humans to recognize sounds at very long distances. To understand why far-field sound event detection is such a challenging task for machines, we should remember that acoustic waves undergo absorption and reverberation depending on the propagating medium, combined with attenuation due to geometric spreading. This classical 1984 paper by Bass and co-authors gives the absorption coefficient of the atmosphere. You will notice that absorption grows linearly with distance and exponentially with frequency, with corrective terms that depend upon hygrometry and air pressure. And to understand how humans cope with these changes in absorption, we need to take a look at auditory neurophysiology and the functional organization of the cochlea. As you know, the basilar membrane of the cochlea comprises inner hair cells whose stereocilia play the role of bandpass filters. The center frequencies of these bandpass filters grow monotonically from the apex to the base, hence a continuous relationship between physical frequency and pitch sensation that is known as tonotopy. And here, of course, you recognize the biological equivalent to a time frequency decomposition. But the story doesn't end there. The stereocilia are surrounded by so-called outer hair cells, whose role is to amplify or reduce mechanical vibrations by contracting or elongating, under the modulation of a neurotransmitter named acetylcholine. In this way, outer hair cells enable a form of top-down control on the electrical signal that gets transmitted to the auditory nerve and eventually the cortex, the brain. So now let us examine how we could mimic this property of loudness adaptation in a machine listening pipeline. Consider an audio signal X and its spectrogram EX. And here under the word spectrogram, you're free to imagine your favorite time frequency representation, be it short-term Fourier, Mel-scale filter bank, or constant Q wavelets. Multiplying X by some constant K results in amplification if K is larger than 1. And of course, here what we have is a commutative diagram, meaning that the spectrogram of Kx is tantamount to a multiplication of Ex by K. The gist of loudness adaptation is that for values of K close to 1, Ex and Ekx should map to the same representation. This is a form of calibration in the sense that we're not trying to undo the scaling by K and recover Ex, but rather to produce a representation phi of Ex, which is invariant to the value of K. Likewise, we expect phi to calibrate the spectrogram Ex with respect to an equalization filter H, as long as its frequency response H hat, or modulus of H hat, is close to identity. Here, the diagram is not exactly commutative, but only approximately so. But in any case, we seek phi such that phi of Ex is equal to phi of Ex convolved with H. In 2017, Wang and co-authors have proposed a parametric computational model for phi under the name of Per-Channel Energy Normalization, or PCEN. To be clear, the word channel here does not refer to left-right channel as in stereo audio, but rather to a frequency channel as in radio channel, for example. And PCEN consists in two stages in a cascade: adaptive gain control and dynamic range compression. In the interest of time, I will not walk you through all the operations, but suffices it to say that PCEN has 5 parameters: delta, epsilon, phi t, alpha, and r, as shown here, and that they can be predefined in advance or learned via gradient backpropagation. If we leave aside those parameters for a minute, we end up with what is perhaps the simplest possible formulation of PCEN: EX over MX, where MX is a moving average of EX across the time dimension. This moving average operates on a per channel basis, hence the name PCEN. Let us reflect on the response of PCEN in the presence of noise. And here I will be taking the word noise in the sense of second-order stationary processes, as a signal whose short-term periodogram varies slowly. In this context, the computation of MX resembles a method of averaged periodograms, also known as Welch's method. And thus, we expect the ratio between EX and MX to be around 1. On the contrary, near a transient region, EX suddenly becomes much bigger than its moving average, and the value of phi of EX, of PCEN of EX, is large in front of 1. We need to observe that this distinction between noise and transient is, again, invariant to amplification by multiplicative factor k, and equalization by convolution with some impedance curve h on the signal x. Now here is what PCEN does in practice to a real-world recording of bird sounds taken from the bird Voxful night dataset. On top, we see the log-mel spectrogram of the acoustic scene showing 2 sources of noise, insect stridulation around 4 kilohertz, plus a passing car between 10 and 15 seconds. Applying PCEN to this time frequency representation reduces the influence of these 2 sources while enhancing the saliency of transient events of interest, in this case, avian flight cars, passerines. Now that we have visualized PCEN on one short example, we may scale up the study and take a look at how it performs on a diverse dataset. With colleagues from NYU and Cornell, we've compared the covariance matrices of Mel frequency spectrograms before and after PCEN. We've repeated the process on acoustic sensor networks, Sonic, DK's 2013 SC, and BirdVox. The results are visually clear. PCEN equalizes and decorrelates subband activations in the spectrogram, thus bringing the covariance matrix between frequency bins, between channels, closer to identity. Another important metric worth visualizing is the histogram of magnitudes in the log-Mel spectrogram versus in the PCEN Mel spectrogram. And these magnitudes, of course, correspond to grayscale color values on the display. Across data sets, we observe that PCEN brings the histogram closer to a Gaussian. Although this phenomenon is not yet fully understood from a theoretical standpoint, we may already affirm that this Gaussianity yields a benefit in statistical robustness when we train machine learning models on PCEN processed data. We have replicated the study on different sensor locations from the BirdVox project and found that PCEN calibrates the activations of each sensor to the same mean and same standard deviation. However, there is a caveat here in that the 5 parameters I told you before, alpha, epsilon, phi, t, delta, and r, need to be adjusted to the task at hand. Reusing optimal parameters, this combination of 5 parameters from a speech recognition task, for instance, doesn't work nearly as well. And now to go full circle with my first slide, my co-author Ellie Knight has recorded vocalizations from the common nighthawk at different distances, ranging from 30 meters up to 500 meters. So this is really the same call traveling through an atmospheric medium. In each display, the white dot denotes the time frequency region of maximum contrast. We observe that as distance increases, this white dot jumps erratically from one region of the call to another, typically from the onset to the offset and back. In comparison, the dot remains stable up to 300 meters, from 30 to 300 meters, in the PCEN representation, the right column, second and fourth column. And this is because, as we've seen, PCEN is robust to the effect of atmospheric absorption induced by some impulse response H. As of today, PCEN is a component in the state-of-the-art acoustic front-end for automatic speech recognition, namely LEAF. Learnable audio front-end. LEAF was published earlier this year by Nel Zegidour and co-authors and comprises a filter bank of Gabor-like filters with learnable center frequencies and bandwidth parameters, followed by PCEN, again with learnable parameters. And the authors have achieved state-of-the-art results in many other challenging tasks besides speech processing, birdsong detection, musical instruments, and the list goes on. And I invite you to read their paper for further details. In conclusion, the past 3 years have witnessed a surge of papers using PCEN very creatively to address diverse machine listening problems. Here's a non-exhaustive list spanning urban noise, industrial noise, and bioacoustics. Unfortunately, I don't have the time to discuss all of it now, but I devote one section of my paper to reviewing them, and I invite you to look more into this. But to begin with, if you feel like trying out PCEN on your own data, my recommendation is to start by downloading the Librosa Python package and follow the instruction from the librosa.pcen function. Many thanks to Brian McPhee for maintaining that package. Looking forward, I can identify 3 avenues of research in which PCEN has yet to show its full potential. 1, we need a better understanding of the role of every hyperparameter, especially T and alpha, and especially regarding the effect of Gaussianization I have shown earlier. 2, we need more efficient implementations of PCEN on integrated and on embedded hardware. These implementations need to operate with low precision arithmetic and intermittent energy supply while remaining numerically accurate for downstream applications. 3, and this is the more speculative kind, I believe there is a motivation behind making the hyperparameters of PCEN, delta, epsilon, phi, t, alpha, and r, making these parameters sensor dependent and time dependent. So not just depending on frequency, but also on time and a sensor, so as to improve its ability to calibrate spectrogram magnitudes in the presence of non-stationary and non-uniform noise. Thank you.